This video is going to be all about ideal gases, ideal gas equations, universal molecular gas constants, which was obtained experimentally, how we can link the kinetic theory to derive molecular equations, and how we can link it towards the macroscopic gas particles. We're going to talk about things like the Boltzmann constant, translational kinetic energies, and more. So let's begin. What are ideal gases, first of all? Now, to explain that, I want to look at this right here. So basically, if you had watched my previous video on the gas laws, and I highly suggest you do, you would have known that the volume of a gas is actually directly proportional to the temperature of a gas, and this is Charles' law. Charles' law tells us that for a fixed mass of gas in certain fixed pressures, as you increase the temperature of a gas, then the volume of the gas would also increase. And so if they're directly proportional to each other, then this is the graph that we would draw. Because they're directly proportional, they would actually pass the origin at a point. And think about that for a moment. Remember that this is the thermodynamic scale, this is the Kelvin scale, it's not the Celsius scale. When the Kelvin scale reaches 0, the ideal behavior of a gas, according to Charles' law, is that the volume of the gas should also become 0. It should pass the origin. Now, that's a little crazy, and you're probably right. It doesn't really happen in real life. Now, why doesn't it happen like that? Well, this is a graph of nitrogen gas. And what happens to nitrogen as it cools down near 77 kelvins is that it actually suddenly drops by a lot in volume. And that is because nitrogen condenses at 77 kelvins. Its boiling point, aka its condensing point, is 77 kelvins. So no, it never reaches the 0.0 in a perfectly straight line that is directly proportional. So this is actually what happens in real life. Now, the ideal gas equation is that rho v divided by T equals constant. The pressure times the volume divided by the temperature is a constant. And that's what we've linked together last time. We've linked every single 3 of the laws together and gotten this law. And however, this is often not the case in real life, as gases tend to condense into liquids and then into solids as temperature gets colder, like the example shown with nitrogen. And so that's true. What we're saying here is that this only is true for this range. As the temperature gets cold enough to go into its changing states temperatures, this will not hold true anymore. Hence, we can say that the ideal gas is a gas for which we can apply the equation rho v divided by T equals constant. An ideal gas will reach the origin, 0.0. And so that's basically all it is. It doesn't really exist in real life because the matter that just doesn't disappear completely as you go towards 0 in real life, and it will go through different changes of state that will mess up this whole entire direct proportionality of the equations. However, we can imagine that this ideal gas would actually follow this law, and that's why it's ideal. So now we're going to take a look at the ideal gas equation. As we've previously seen, we know that rho v divided by T equals to a constant, right? Let's put constant as a K. And what we're trying to do with this ideal gas equation is that we're actually trying to figure out how to calculate this constant. Now, constant is actually nR. That's what we can see over here, nR. What they individually represent is the N represents the moles of an ideal gas. The R represents the constant of proportionality, and it has an experimental value of 8.31 moles per kelvins. Now, this value, what it means by an experimental value is that you just found it through experiments. So you've basically given a couple of moles their own pressure, you've measured their pressure, you've measured their volume, you've measured their temperature, and you've done this for many, many different samples. And this value is always the same. The constant of proportionality is always 8.31 per moles per kelvins. So that's very interesting. It follows these two. And then now that you know these, you can actually calculate the pressure, temperature, and the volume of any gas sample ever, assuming that this is an ideal gas. So this experimental value holds true for all gases. The only requirement is that they are ideal. Now, assuming that you have taken chemistry, moles are probably a very standard piece of knowledge to you. To calculate the number of moles, which is N, we do the number of moles is the mass in grams of the sample of gas divided by the molar gas, which is gram per mole. So the molar mass is very, very easy to calculate. The molar mass is basically, for example, if you have carbon-12 basically has 12 nucleons. So it has 12 protons plus neutrons. And basically, 1 mole of carbon-12 is going to give you 12 grams. So basically, if I have 24 grams of carbon-12, then how many moles do I have? Well, 1 mole is 12 grams, so you divide that by 12, you get 2 moles. It's as easy as that. We're going to solve an example question. For example, the volume occupied by 1 mole of an ideal gas at room temperature, which is 20 degrees Celsius, and pressure, and this is the ideal pressure, and this is pressure at sea level, which is actually also 100 kPa. You can round it up to that. So what we start out by doing is we state this equation, and this is the ideal gas equation. PV equals nRT. And then we're trying to find the volume. So we kind of put this over here, and then we get the row on the bottom. So the volume equals 1 mole, which is 1 mole here, times the constant of proportionality, 8.31, times the temperature. And the temperature is basically 20 degrees Celsius. Now, remember what is really important about the ideal gas equations is that all of the temperatures are measured in the Kelvin scale. So temperatures are measured in the Kelvin scale, thermodynamic scale. And so that means we have to convert this Celsius temperature into the Kelvin scale. So what you do is you basically just add the 273.15 kelvins to this temperature, and then you're going to get the answer. You can check out my video on the Kelvin scale if you would want to. So we do that, and then we just divide it by the pressure, which is already given here, and then you get the equation, which is extremely easy. Now, this one decimeter, we also use this quite a lot in chemistry. 1 dm cubed is basically 1 times 10 to the power of -3 meter cubed. Because 1 decimeter is basically 10 meters. So if you do this, because you're cubing it, the 10 basically also gets cubed, and that's why we have a difference in thousandths. Okay, so now that we've gotten to know the ideal gas equation a little bit, let's talk about it. So rho v divided by T is an empirical equation. What does an empirical equation mean? It means that it was obtained experimentally. As I've just explained, people just did this. They gave different values of pressure for different moles of gases, and then they just got the values and the constant, which is 8.31, and that's all they did. So this also means that it doesn't explain why gases act in this way. The way that they found this wasn't through thinking about how gases moved, like looking at the core of molecular behavior. They did this by just testing again and again. So now we're going to learn how to actually think about it in a way that actually explains why gas behaves like that. So we can talk about pressure first. Let's set some boundaries. Pressure is actually from collisions. Now, pressure is made by gas molecules colliding on the walls of a container, and that basically results in a change in momentum, and that exerts a force on the outside, towards the outside of the container, and that's what pressure is. Pressure is force divided by area. Temperature is the kinetic energy of the molecules, as we have seen in a previous video. And that previous video was about internal energy. So the kinetic theory of matter links the microscopic properties of particles with the macroscopic properties of a gas. What does that mean? Well, gases are basically composed of all of these tiny little molecules. And if you put them all together, you can't really see them. We'll just have like a cylinder of gas. And when we look at the cylinder of gas, we can get its temperature, you can get its volume, its pressure, but you can't get the temperature or the volume or a pressure from these tiny little molecules. What can you get from these molecules? You can get their mass, you can get their velocity or their speed, and then you can also get their kinetic energies. So what we're trying to do right now is to link this with this. What happens on the microscopic scale of the tiny little scale of these tiny particles that makes sense to explain the big ones that actually you can measure when there are millions of molecules together, billions even. So we're going to use these assumptions, and we can use Newtonian mechanics to show that pressure is inversely proportional to volume, which is Boyle's law, temperature, Charles' law, and pressure is directly proportional to the temperature, which is pressure law. So we're going to explain the previous gas laws that we found in a microscopic manner. So using the kinetic model of matter, we can also show that the particles of a gas have a range of speeds. Some are faster than others, and you're all going to come to these conclusions at the end of these videos, or this video actually, to be specific. So before we start with anything, we're also going to lay some more groundwork and some more assumptions. Let's go to the first one. If the forces between particles are negligible, except during collisions, then these equations would hold. So basically, we're going to say that the forces between particles that are in a gas are negligible. We're going to pretend as if they are zero. I mean, obviously, during collisions, when they become very close to each other, there's going to be a little bit of force action. Now, if it wasn't, then the particles would clump up together in the middle of the gas. The particles travel in straight lines between collisions, showing that there is no force acted on them that is significant. Secondly, the volume of particles themselves are negligible, which is to say that compared to the volume of the gas, this is because they are so spread apart. So basically, the particles are so small that their individual volumes are basically counted as zero if you compare them to the amount of space that they take up as they travel around the place. And this is because they are very, very spread apart. They move much more and over much greater distances than their own volumes. So this is because, and we can also get this from when liquids become gases, they also expand immensely. And that's how we can tell that the particles really do spread out a lot as they become gases. So we're going to pretend as if the volumes of the particles themselves are zero. Most of the time, the gases travel in straight lines. The time of collision with another particle is negligible compared with the time between collisions. The time that they spend in contact with each other, in contact with the walls, etc. is very, very small because it's a collision after all, and also they travel in between collisions for too long for that time to even be something significant. Next is that the collisions between particles or the walls of the container are completely elastic, which means that no energy is lost. This means that kinetic energy cannot be lost because the internal energy of the gas is the total kinetic energy of the particles. Now, internal energy is consisted of potential energy as well as kinetic energy. And for gases, the potential energy, you can say that it is zero because they're so far away from each other that the forces are very negligible. So that means that their entire internal energy is kinetic energy. Energy cannot be created nor destroyed, and hence the collisions are completely elastic. And in an elastic collision, no kinetic energy is lost. And relative velocity is also constant. So when gases are close to condensing, it is very different. A little above boiling point temperatures, and that's where they're close to condensing, right? They haven't condensed yet, but they're going to do it soon. The gases move more slowly and they tend to stick together, so the kinetic theory of gases must be modified. And this is why we, in this level, deal with ideal gases instead of talking about real-life gases, in which we have to modify the kinetic theory of gases. So those were the assumptions that you should have made in order to carry on with this chapter. Now let's derive it. So let's derive microscopically the pressure of a gas, and we're going to get the ideal gas equation by ourselves mathematically. So picture this cube that I've drawn right here. Let's picture a single particle of mass, m, that is traveling in a cube of length, L. It has a speed, c. So that is the particle. It has mass m. It's traveling in this length L, and also it has a speed of c. As it rattles within the box, it contributes to the pressure of the gas, because the pressure is the force from collisions with the walls of the box. So let's say that the particle collides with one side of the box. It rebounds elastically, and so its new velocity is negative c, which means that absolutely no kinetic energy is lost at all. That's why it has the same kinetic energy. As it goes here, it has a velocity of c. It comes back perfectly elastically rebounding, negative c velocity. Its momentum change is from mc to negative mc. Momentum is mass times velocity. So the initial momentum was mc. Final momentum is negative mc. Momentum is a vector quantity. So the change of momentum is basically the new momentum minus the old momentum. And that is negative mc minus positive mc, which is negative 2mc. So that's the momentum change. Now the distance traveled is 2L because it's gone from the length of the box here towards the length of the box here. So that makes sense that it's 2L because the length of the box is L. So the speed is c. So basically the time taken between collisions, basically we know that the velocity is distance traveled divided by time taken. So time taken is distance traveled divided by velocity. Distance traveled is 2L. Velocity is c. So we get that, and that will basically give us time. Now that we have time, and we also have the total momentum change. Remember that the total momentum change that we got last time was negative 2mc. So the rate of change of momentum is basically momentum change divided by time taken, which is momentum change, negative 2mc divided by time taken, 2L divided by c, which is negative mc squared divided by L. Now, we're going to say that this is going to be just mc squared divided by L, not negative, because we know that the rate of change of momentum is actually the resultant force, and we can get that from the Newton's second law of motion. So we're saying that the force that it exerts outside, and what I'm saying is, if this is the wall, and if this direction is positive, this direction is negative, because this is positive c, negative c, as it goes like that, that means that what we're trying to get right now is the force that is exerted outwards. That is in the positive direction, and that's why we're going to make it a positive force, because it's going outside. Now, if it was going inside, and that's the force that the wall exerts onto the particle, then it would be negative. But we're not talking about that. We're talking about the force that the molecule exerts outside onto the container. So that's why this negative, it's gone. So we make it positive because we are talking about the force that the positive particle exerts on the cube side. The area is L squared. So basically, the pressure is the force divided by area, which is mc squared divided by L divided by L squared. And so finally, we get that the pressure is mc squared divided by L cubed. However, this is only for one molecule, but there are larger numbers of molecules, which is n, in the box. Each have different velocities. Hence, we put the average velocity of the c squared as this. So we put it in these brackets, and that is basically what that means, is that it's the average of all of the velocities. So basically pressure is n, which is n number of molecules times their masses times their average velocity squared divided by L3, because what we're trying to change is the mass. We're trying to change the mass, and the average velocity is going to become just basically the average. And so basically the mass, you're going to have to times how many molecules there are onto there. That's the only thing we got to change. But this assumes that all molecules are traveling at the same direction. So we divide it by 3 because they're traveling in 3 different dimensions. And so we have L cubed is actually the volume of a cube. L cubed, it would give us the volume of this. So basically, what we're going to say is we're going to divide this by 3 because pressure is actually in all 3 dimensions. And that's why we have to say that we're going to divide it by 3. And then we're also going to replace this L with the V to make it simpler. So we get the final equation, which is that rho slash pressure is 1 out of 3 nm average velocity squared divided by volume. Now, you can also say it in this way. Or you can put the v over here and then you can get this equation. And that's it. Now, to simplify it even further, nm, which is the number of particles times the mass of one individual particle, we can just say that that's total mass, and we can denote this by a capital M. So basically, nm divided by v is actually mass divided by v. That is basically density. So that's rho. So basically what we're trying to say is that we can replace this whole entire thing with rho, which basically stands for density. So P, which stands for pressure, is 1 out of 3 rho c squared. Now, so the pressure of a gas only depends on the mean sample of speed of its molecules and its density. Let's talk about why the equation makes sense. Pressure is directly proportional to the number of particles. That is because more molecules means that there's more collisions, and that's obviously going to increase the pressure. Pressure is directly proportional to the mass of a particle. More mass means that you have a greater momentum change per collision, and hence a greater force exerted on the walls, and hence greater pressure. Pressure is directly proportional to the square of the speed. Now, that also means that you have more momentum change, and also it means that you have collisions more often within a given time frame. So because you're traveling much faster, you have more collisions in a certain time. And lastly, we have pressure is inversely proportional to volume. When you have a bigger volume, you have more time spent by the molecules in the bulk of the gas, which means that there are less collisions. Let's say there's a bigger volume, the gases are going to spend more time in the middle of the gas, traveling around before they hit it. When you have a smaller volume, the gases at the same speed are going to travel much faster to hit the walls, and therefore there's going to be more collisions per second, which means that the pressure is going to be higher. So if you really think about it, this equation does make a lot of sense, and you can actually explain it using each of the constants and how they are related to each other as well. So now we're going to basically bridge the gap between the microscopic properties and the macroscopic properties. Now, we've previously come up with this equation. Pressure times volume is basically 1 out of 3 nm times the average velocity squared. And we know this from the macroscopic equation that we found out with the gas laws. Now, they both equal PV, so we're going to equate them to each other. 1 out of 3 nm velocity squared equals nRT. And so we can move this around a little bit, and we know that basically we get this. Now we can take a look at this right here. This is total number of molecules. This is the number of moles. In 1 mole, there are basically the Avogadro's constant number of molecules, which is 6.02 times 10 to the power of 23. So basically, we know that because the total number of molecules divided by the number of moles is basically going to tell you that you're going to get the Avogadro constant. Why is that so? Because the total of number of molecules is going to be this times something, and that is going to be the number of moles. And you divide it by the number of moles. You get that. So that is that. We have replaced this by Na, and I had to multiply 1 out of Na like that because of the fact that they are switched around from this. And then so we've divided the entire equation by 1 out of 2. Why is that so? Because we see mc squared, and that is basically mass times velocity squared. That's very familiar, and that's because of 1 out of 2 mv squared. That gives us kinetic energy. So we divide the entire equation by 1 out of 2, so to get the familiar equation for kinetic energy. So finally, we get 1 out of 2 m velocity squared is 3 divided by 2 RT divided by the Avogadro's constant. Now, what is very interesting is this constant of proportionality, R, divided by the Avogadro's constant is the Boltzmann constant. So we have a new constant coming in, and this is denoted by K. Its value is 1.38 times 10 to the power of negative 23 joules per kelvins. That's the Boltzmann constant, and we're going to use it to replace this. So 1 out of 2 m velocity squared is 3 out of 2 kT. That is the Boltzmann constant. Now, this is basically the average kinetic energy. So basically, we finally get the conclusion, which is that the mean translational kinetic energy of an atom or molecule of an ideal gas is proportional to the thermodynamic temperature. We get that Ke is directly proportional to the temperature. And this whole entire thing, that is a constant. 3 out of 2 K, that's a constant. These are variables. So basically, we say that these are directly proportional to each other. That's the conclusion. Okay, so we're almost done. We're going to talk about what the mean translational kinetic energy of an atom means. Translational kinetic energy is the energy that the molecule has because it is moving along. A molecule made out of 2 or more atoms may also spin or tumble around. They are then said to have rotational kinetic energy. This is a monatomic atom, and this is a diatomic atom, and they're going to roll and tumble around because of their little uneven masses, and that's why we say that they have rotational kinetic energy. We can also talk about the mean or the average translational kinetic energy. We can do this by adding up all of the kinetic energies of individual molecules and getting the average, or watching an individual molecule over a period of time as it moves about and calculating its average kinetic energy over this time. Because it's going to obviously go through different speeds during a certain period of time, we can just take a look at an individual molecule and use it as a representative as well. So the Boltzmann constant, it tells us how a property or a microscopic particle tells us about the macroscopic property of the gas. And basically, it's going to link together the kinetic energy of a certain tiny particle and how that translates over to the whole temperature of the whole cylinder of gas. So this is why its unit is joules per kelvins. The unit of the Boltzmann constant is actually very, very small. It's 1.38 times 10 to the power of negative 23. What does this tell us? Well, it tells us that the average kinetic energy in joules and the change of that for a given temperature change is very, very small. So if you go up by 100 degrees Celsius, the kinetic energy change you're going to get out of a gas is not that big. It's actually extremely small. Average kinetic energy is 3/2 kT, and that's something you can use to memorize our little equation. Now, finally, if we double the thermodynamic temperature, then that means that we're going to be doubling the kinetic energy, because the temperature is directly proportional to kinetic energy, but it doesn't mean that we're doubling their speed, and that's very important because kinetic energy is 1 out of 2 mv squared. So basically, Ke is only directly proportional to v squared, not v as a whole. So actually, we're going to times it by square root 2. So yeah, that's something to remember. In a sample of air, and in sample of air, we have a lot of different airs, like air molecules like nitrogen, we have oxygen, we have carbon dioxide, we have argon, etc. They have different masses, but all of them have the same kinetic energy. That's very important. In a sample of air, disregarding their masses whatsoever, all molecules will have the same kinetic energy as they constantly collide with each other and they share their kinetic energy together during these collisions. However, this also means that heavier molecules travel slower because kinetic energy is 1 out of 2 mv squared. Everyone's kinetic energy is the same. If this goes up for you, this will go down for you. So that is about it towards our video on ideal gases. It was a very lengthy video on many different topics to touch on, but essentially as a summary, we have talked about ideal gas equations in the general macroscopic scale. We've talked about what the universal molar gas constant is. It's an empirical constant. It was derived through experiments. We've talked about how we can link the kinetic theory or the kinetic molecular theory, and we can derive the macroscopic theories. We can derive this tiny little microscopic one and link it to a macroscopic equation of this. And we can also get the Boltzmann constant. We've talked about what it was, and we've talked about stuff like mean translational kinetic energy, etc. So I hope this video was helpful to you in any way. That's all for this video. Thank you for watching, and check out my channel for even more physics.